Good, then maybe I can just say a few words. I'm happy to host the EMBL Bioimaging Seminar series again today, and I want to say good morning or afternoon, depending on where you are. So first of all, I wanted to make a brief announcement, which is that we as the organizers, we decided recently to slightly expand the reach of the seminar series, and we've therefore invited both folks from the Allen Institute and from UT Southwestern to join us. So warm welcome to everyone. Um, and with this, we also hope to not only increase the participation, but maybe also to get a few new speakers. So it's a little bit to fresh up the mix. And so today we have Rory Power from EMBL join us, and it's my great pleasure to give a short introduction to him. So Rory is a senior engineer at the moment here at EMBL, working at the Imaging Centre in Heidelberg. But Rory actually has a PhD in physical chemistry, as I also only learned very recently, from the University of Bristol, where he actually did holographic optical tweezers to study aerosols. And he then continued his career as a postdoc, first at the Max Planck Institute in Dresden and later in Morgridge at the University of Wisconsin at the Morgridge Institute, where he worked in both cases with Jan Huisken, who I think many people here know. And he worked with Jan to develop, of course, advanced light sheet microscopes, including the by now very famous Flamingo platform. But since 2020, he's actually at EMBL, and we're very happy to have him as one of our key colleagues here because he's been certainly instrumental in advancing not only light sheet microscopy, but also single molecule localization microscopy for the sort of use as a service in our advanced imaging facility. But I'm pretty sure he will talk more about those 2 or 3 projects in the next 45, 50 minutes. So with this, Rory, please, the floor is yours. I'm looking very much forward to your presentation.
Okay, great. Hello, thank you to whoever's here, and great to have the opportunity to speak to you today. I will talk, as Robert said, about the advanced custom microscopes I've been setting up for service at the Imaging Centre. So actually, I will talk about 3 microscopes rather than the promised 2. So that's within the Imaging Centre itself and also the research groups at EMBL. So I get into it. So for those of you that are not aware, the EMBL Imaging Centre was opened in 2021. So it's an effort to make the latest light and electron microscopes available for the sort of wider life science community. So we have this nice building, hopefully you can see here. And this was custom built for purpose. The main bulk of the microscopes are sat on an enormous block of concrete, which makes it extremely stable for doing very high resolution imaging, such as the high end kind of cryo-EM and MinFlux on the light microscopy side. We do not operate as a facility in the classical sense, so we're not training users and then letting them loose on microscopes. Rather, this is kind of a full tailored project support deal. So external scientists, primarily external, would apply to come and use instruments, and then they would be kind of handheld through the whole imaging process from sample preparation through actual imaging and eventual processing and analysis of the data. Beyond that, one of the major kind of remits of the center is around innovation and commercialization of, or let's say at least tech transfer of the kind of, what's the word? New imaging technologies from the research labs at EMBL, let's say. And yeah, and that's really the area that I'm primarily working on and what I'll talk about today. So as I said, it's primarily an external facing imaging center. Most of the user base is from institutes outside of EMBL, but inevitably with the more sort of custom tech developments, we get a lot of input from not only the sort of more engineering focused groups at EMBL, but also the biological groups provide a lot of the applications. So I focus entirely on the light microscopy side of things, but a pretty large focus of the center is also on the cryo-EM side, and then the sort of where this meets with light microscopy. So a big focus is kind of the correlative side of things, so CLEM workflows and so on. We have from our user project so far, like samples spanning all of these length scales from, greater than millimeter sized tissues through embryos, organoids, organisms, cells, everything down to viruses. The sort of smallest thing I talk about today is on the scale of like protein complexes, and then beyond kind of into the world of the cryo-EM side of things. And the applications from the users span a similarly wide range of sort of applied and basic sciences as well. So, where does engineering sort of fit in here? So, yeah, my job is an engineer at the Imaging Centre. What this means is building up custom imaging systems. I've tried to split the kind of whole sort of life cycle of a project or from into this chart here from sort of microscope design or engineering side of things, application and analysis. And really what I'm involved in is these things primarily in green. So the design of microscopes, having parts made, with our workshops and so on, construction alignment and so on, and into cycles of revision and maintenance eventually. And I'm sure most people are pretty aware of this, but this kind of encompasses all these areas of engineering with which I'm, to a greater or lesser degree, vaguely competent in. So it's quite a lot of things to cover, but that's essentially what I am doing. The actual technologies we offer for service on the light microscopy side of things is sort of divided into these 5 sections. So super res, nonlinear, in vivo, multiscale, and micro dissection. And I'm just going to talk about 2 of these today, which is where my work is focused, which is the super res and in vivo side of things. So yeah, I suspect I'm probably preaching to the choir a bit with this, but why actually do custom microscopy development for service? Well, commercialization is typically fairly slow. And, when something actually turns up, the solution may be too inflexible or not exactly what, the users want, or just not really state of the art anymore. So I provide this example here from EMBL, so the sort of archetypal modern light sheet microscope, the SPIM, which was built by my ex-supervisor Jan Huskin at EMBL in Ernst Stelz's lab, was reported 2004, and it took another 8 years for Zeiss to sort of commercialize this, although obviously there'd been some developments in the meantime, but this took quite a while. So beyond this, sort of EMBL's specific reason is we have very strong microscope development in the research labs. So I've highlighted some key people here. We want to be able to retain the technologies that they're developing and the knowledge. So obviously there's a lot of turnover of research groups and things. We want to be able to kind of maintain these things in-house long term, as particularly when people leave. So for example, Jonas Rees on the super res end of things recently left. And ultimately we want to open up the technologies these labs develop for the outside users. So whereas they may be comfortable with sort of small scale collaborations with individual labs, it's not the sort of goal of the research labs to be providing like actual service. So that's where the Image Centre comes in. And yeah, we're well supported by great workshops at EMBL as well, which is very helpful. Okay, so I'll just start by talking about the super res side of things here. In terms of what we have before the custom microscopes, there's several MinFlux systems, plus 2 SPED systems from Leica that we have in regular use in service. And then so a fairly clear gap in the sort of imaging portfolio in between these 2 resolution-wise is single molecule localization microscopy. And this has historically been a strong area for EMBL with, as I said, Jonas Rees's lab. And with him, just leaving, this seemed like a good thing to be able to have for service. So yeah, Jonas has been working on specifically 3D single molecule localization microscopy for applications in structural biology. So it's kind of like imaging at the scale of the protein complexes, like I showed. Generally, the commercial options don't deliver the same performance. That's just, I think, fair to say, at least at this scale of resolution. And like I said, it's complementary to what we have already at the imaging center in terms of the other systems. I think everyone probably knows the general way that localization microscopy works, but if not, we have this picture, this demonstration here in this blinking lights of the Eiffel Tower. So you see, if we localize each emitter, we can build up a super resolution image of the Eiffel Tower from the sort of stochastically blinking lights. Well, I guess they're not stochastic, but so in the case of this can in real sort of biological samples, this sort of sparsity of emitters is achieved either through photochemical means in the case of palm or storm, or transient on-off binding of fluorophores in the case of like DNA paint or whatever. So when I started in EMBL like mid-2020, then sort of within a few months, we'd come up with this plan that we would implement a sort of 3D SMLM system in the imaging center. Helpfully, of course, there's a Jonas's lab there, and I inherited a lot of great stuff from that, which kind of, let's say, made this fairly daunting prospect a little easier. So at least on the control side of things, we had this nice micromanager GUI, also micro FPGA, which is a hobby-based FPGA system for hardware synchronization. On the analysis side of things, we had the super resolution microscopy analysis platform SMAP. So kind of from that side of things, we were really well covered. So the SMAP is important for doing a lot of the kind of on-the-fly analysis of the particularly D-Storm data for sort of quality control before one's taken hundreds of thousands of images and so on. The one thing that really was not so well defined is kind of the mechanical and optomechanical side of things. So of course, I managed to dig this CAD rendering out of the supplementary information of a paper, but this was a little bit more, the area was a little bit more up in the air. So I kind of embarked on a full redesign or design of the system from scratch. I did a lot of optical simulations and simulating a lot of objective lenses from patents and so on, just to come up with a few ideas of how to build a nice system. And yeah, I'll show a lot of these kind of beam schematics today, I should say, given that I'm the engineer at the imaging center. It's not too much in the way of biological data today, but if you like beam paths, there's plenty of those. So this kind of shows a schematic of the 3D SMLM system. We have a microscope body kind of at the top where the objective is. Then this is the sort of pathways I developed. So there's a homogenized illumination system, which is based on a refractive beam shaper. And then this is compatible with high-low and turf illumination, which is pretty important for us. I also developed a system based on sort of telescopic arrangement of lenses on stages to be able to variably change the illumination spot size. So again, for like D-Storm imaging, which is very power hungry, you kind of want to achieve a higher radiance at your sample without burning out your objective lens. So generally, or often, actually, the optimum solution here is really just to reshape the size of the illumination spot. We do this with lenses rather than just throwing away laser power on irises or something like this. So this is helpful. And then for the people who don't need such high radiance, like for DNA paint, you can have a very large field of view and things like this. So this is nice for the service side of things. We have high NA silicon and oil objective lenses. On the emission side, implemented sort of a spectrally discriminative image splitter. You can see down the bottom. So this is essentially, again, primarily for D-Storm imaging. All of the dyes that work well for this are in the far red region of the spectrum. So talking like 650 to 750 nanometers, and therefore heavily overlapping with their spectra. So In order to do multicolor imaging, what we do generally is, again, exploit the kind of sparsity of available in a localization microscope, image a single emitter into two spectrally distinct channels, and then by calculating the ratio of intensity between the two channels, we can identify the dye species that gave rise to the emitter, or that the emitter is. And by this method, we can kind of do, let's say, 3 to 4 heavily overlapping fluorophores in DStorm. So this is something that the users are commonly doing. Also on the emission side of things, there's a tunable astigmatism module. So the 3D in the 3D SMLM in this case comes from astigmatism, so the sort of distortion of the point spread function along two orthogonal axes that encodes the Z position of a molecule. In this case, I implemented this with a pair of cylindrical lenses, so it's a positive and a negative cylindrical lens that essentially, when the axes are aligned, there's no astigmatism or negligible, and then if you introduce a small rotation between the two axes, you can controllably induce a sort of amount of astigmatism appropriate for what you want to do, and this allows it to be optimized for different samples, different depths of imaging, different objective lenses, and so on. Again, towards kind of service, this is very helpful. So this typically works over a range of like about 800 nanometers in terms of, yeah. For localization microscopy, it's generally we're taking tens to hundreds of thousands of images per rendered super resolution image. So it needs to be very stable. I mean, this is taken care of partly by, I would say, pretty solid mechanical design. But also we have a infrared laser-based focus lock system, total internal reflection of a laser from the cover slip as a kind of laser rangefinder, which is then the back reflected beam is then collected on a quadrant photodiode. And then, yeah, the sort of signal from this is then used to drive the piezo to maintain the spacing between the sample and the cover slip. And this works with a precision on the order of about 10 nanometers. Yeah, there's many components in here that are motorized. So the cylindrical lens can be moved in and out. There's a Bertrand lens in front of the camera, which allows you to look for bubbles in the oil, which is very helpful for quality control and so on, and various other components that are just moved in and out of the beam path or positioned through software. So there's no manual interaction required on the part of the application specialist or the user. And yeah, from the kind of control and GUI side of things, there's a lot of nice smart automated features around kind of like DStorm imaging again. So automated control of the UV pulse length or so on for activation, and to achieve a given kind of emitter density in an image, or for high throughput imaging, one can set up a number of positions and then allow the microscope to kind of decide when each position has been depleted of fluorophores and so on. So yeah, that's nice as well. So yeah, this is kind of what it looks like in CAD. So we have a full configurable CAD model of the system, and this is the system on the optical table. Actually, this is a little out of date, but it doesn't look too much different now. We did a lot of characterization of the system in the context of the nuclear pore complex. So this is a very well characterized reference standard used widely in localization microscopy in particular, as a sort of the benchmark resolution and localization precision and so on. So in this single color at the top, we have so this is Alexa Fluor 647 tagged to the NUP96 via a anti-GFP nanobody. And so the nuclear pore is this 32 protein complex. It's formed of 2 rings, about 100 nanometer spacing across the ring, and 50 nanometers spacing between the 2 rings that are stacked on top of each other. And it has this kind of 8-fold symmetry that we're able to recover quite nicely in the localized images. On a good day, one can achieve localization precisions down to about 2 nanometers in XY and about 8 nanometers in Z. And then the resolution is generally sort of 3 times worse than this. And there's a lot of things that go into determining that, such as labeling density and so on. The bottom, you can see we can do this now also in 2 colors. So this is again the same Alexa 647 label plus WGA CF680. So this is then labeling the sort of interior space in the pore, and you can see that we can resolve this nicely in the 2 colors in 3D, so on. So we were quite happy with this. At this point, we sort of realized we have a fairly complete microscope in terms of like designs from everything from optics and mechanics through software, electronics, and so on. So we decided, we publish this as a protocol, which we did last year. This includes all the CAD and electronics, circuit diagrams, software, and instructions for alignment, construction, you name it, various benchmarking and all the way up to doing this kind of high quality dual color 3D imaging of these nuclear pore complexes via D-storm workflows. Yeah, I did a lot of other sort of characterization here. You can see at the top left, this is the beam shaper, also measuring beam profiles before and after the beam shaper. So you see the Gaussian input and the flattened profile afterwards. Below that, the variable illumination field of view. Then you see the back focal plane images of the objective showing the presence of bubbles. So this is very helpful. Lots of other stuff. Optimized PSFs for D-storm, so optimizing correction color and so on for that. And the optimized astigmatic PSF at the bottom as well. So this all went into the protocols. I think that's all I want to say about the super res side of things for today. It came to some point with this project that it was somewhat nearing operation. So it's the SMLM has been in operation since early 2022. And of course I needed something else to work on. And looking at our focus areas again, the nonlinear side of things was pretty well covered, at least for us for now, by a Leica Dive 2 photon system. The multi-scale and microdissection are likewise covered by parts of our Leica portfolio, so Leica Thunder, etc. And actually the area that seemed the most interesting and actually most well aligned with my background is in this kind of in vivo and intravital microscopy space. So that kind of leads me back to light sheet microscopy. You can see, I mean, I probably imagine most people are fairly aware of this, but light sheet has found a lot of application in developmental biology. So you can see these 4 examples here, two from zebrafish, so the beating heart and the fruit fly development and the C. elegans development as well. It's very fast technique, so it's camera-based, it's wide field, it's very gentle. So in comparison to, let's say, a laser scanning or a spinning disc confocal microscope, you don't have to throw away any light in order to achieve your sort of 3D imaging. And you get this intrinsic optical sectioning because all of the light is ideally at least confined to the depth of focus of your detection objective. So I kind of gave some allusion to there'd been some light sheet microscopy at EMBL since a very long time ago with the original SPIM, also the DSLM which followed, which was the sort of laser scanning or the line scanning version, let's say, of the light sheet microscopy was developed also at EMBL. And then more recently, in the last 10 to 15 years, there's been the movie SPIM, which was a sort of multi-view system for imaging, let's say, primarily, I think it's used for fruit fly development, at least at EMBL. and the InVSPIM from Jan Ellenberg. So this was kind of a system really optimized for medium throughput imaging of early mouse embryogenesis. And this became the kind of the basis for the spin out of the company Luxendo. So these two microscopes became their first two offerings. So that's kind of where how Lightsheet has evolved at EMBL over the years. And actually the InVSPIM development is still an active area of development for Jan Ellenberg's lab at EMBL. So, and that's something I'm working on as well. So actually currently developing or redeveloping, let's say, a dual view InVSPIM for imaging in moderate to high throughput early mouse development. So this is something that was originally started by Dimitri Krom, who you see here, who was in Jan Ellenberg's lab, who got some way with the developing the system during his PhD. I since kind of inherited the project and actually redesigned a lot of it and kind of expanded it to sort of match needs. So it's basically it's a conventional SPIM in a sense, where you have two detection objectives coming from the sides like this. You have one illumination objective coming from below. So they're all relatively high NA lenses. So this is for various reasons that I won't get into, but and then, yeah, we have on the emission side of things, you have splitters in both pathways, and we have 4 PCO Panda SCMOS cameras. So we're doing simultaneous dual color imaging without any sacrifice to the size of the field of view. And we're doing the confocal line detection or the light sheet mode on the camera, on all 4 cameras to sort of improve the contrast. And actually you see for even, so these images in the middle here shown are for a fixed mouse embryo. So top left is the Z intensity projection, and then next to that is the Y maximum intensity projection for the 2 views. If you're splitting it into these 3 volumes here along the detection axis, you see that even for these relatively small embryos, as relatively small, relatively transparent, you still actually do get quite some improvement in terms of like image contrast when you are looking at the kind of near side of the embryo. This is what this looks like in CAD. So this is my redesigned version of the system here. You see the two detection paths with 4 camera views on either side. You see here on the right the 2 detection lenses dipping into this chamber here of these long travel piezo stages and a sample carrier in the middle that's designed for carrying 10 to 100 mouse embryos. And of course, when this is actually in use, everything's covered up and we can have the 37 degrees and CO2 and all sorts of things to keep the embryos happy in culture. So this is great as I said, this is work I'm doing with Jan Ellenberg's lab on the sort of on the research side of things rather than specifically towards service. This is great, and in this very this one use case, this is extremely well optimized. So for imaging mouse embryos or maybe small organoids, this kind of geometry is great and actually maybe absolutely optimum. Likewise for sort of a general SPIM. So I have shown the flamingo here. That is what I was working on in Jan Huskin's lab some time ago. For this kind of traditional SPIM geometry, you would have your embryo in either a FEP tube or in some sort of agarose cylinder, and then dipped into some imaging chamber. And again, this absolutely, I will say, is the optimum, most gentle kind of sample mounting for these types of samples. But for service, it's very specific. So towards thinking about service now, this is good for one thing and perhaps one thing only. And the other issue of light sheet in general is the resolution tends to be a little bit limited by the geometry. So because you have to share aperture between detection and illumination, You are limited in terms of the numerical aperture you can achieve on the detection side. You have to use these kind of longer working distance, lower, kind of less well-corrected lenses, let's say. And yeah, ultimately your resolution is just a little bit limited. So again, for service, we want to have something more general, circumventing these issues. And something I was working on early on in my time in EMBL as well was actually with Robert's lab, co-development of a kind of a hybrid mesoscale oblique plane microscope. So I'll get into what OPM is in a minute for anyone who isn't familiar. But essentially, yeah, this was a sort of hybrid system based loosely around the work of Adam Glaser in terms of adding this additional objective to the kind of conventional single objective OPM, where you use the second objective to provide more effective numerical aperture to launch a light sheet from. In this case, this was, as I say, a mesoscale system. Robert's, I think, application with one of the labs in developmental biology here, so the ICME lab, was to do with nematostellar development. And you see here this is imaging, I think, the volume at once every 2 seconds. And you see these body contractions of the animal that are required for service. So in this case, this kind of imaging geometry is optimal because you don't have to mount your sample in agarose or whatever, and you can allow it to move around in a dish. Like this was designed obviously to be a kind of mesoscale imaging system, and that's not exactly what I was looking towards. So a high resolution version of an OPM at the imaging center would be a really nice thing to have. To understand the sort of technology better and some of the shortfalls, it's all going to be familiar ground, I think, to many of you, but I just need to go through discussion of remote focusing. So oblique plane microscopy is a sort of subset of remote focusing. It lives in the remote focusing family of microscopes, let's say. So remote focusing is a sort of technique described by or implemented by Tony Wilson, I think, in the early sort of 2000s, where you have, instead of one microscope imaging your sample, you have 3 microscopes in series. So yeah, back to back to back. And what it allows you to do essentially is that you can just refocus your third objective here, labeled O3, in order to kind of refocus in your objective 1 space. So it allows you to do volume imaging without any need to either move the sample or the first objective lens, so without disturbing the sample. It gives you this kind of extended depth of field over which you can perform essentially aberration-free volume imaging, which is really nice. So typically, I think 50 times the depth of field of the microscope is fairly reasonable. There's some conditions that have to be met, but this is generally, this is details. So I guess the way to think about it is that when you're imaging either beyond or in front of the native focal plane of your first objective, the spherical aberrations you add when doing this are then directly countered by the inverse aberration when you're refocusing then in your O2 to O3 imaging space. So yeah, so this is nice. This basically gives you a kind of optical replica of your sample in this O2, O3 space, with which you can then refocus your image. Then OPM is basically a sort of tilted form of this. So Chris Dunsby first showed this, that if you tilt your tertiary imaging system, you can actually image a tilted plane across this extended depth volume. And yeah, this is very nice. If you then introduce a light sheet somehow, so via a dichroic or something, illuminate this tilted plane, you can then actually provide some sort of single objective light sheet microscopy, or at least you have one objective at the sample, and you can now do light sheet imaging in conventional preparation, so with dishes on cover slips and so on. If you actually go a step further and introduce a galvo scan system in between the first and second objectives, you can do which is I think the most common form now. You do a kind of galvo scan D-scan type thing where you can scan the light sheet through the sample and descan the fluorescence. So the actual imaging plane state, or the imaged plane, is in focus at statically at the focal plane of the third objective lens. So in doing this, you can do extremely high speed volume imaging. Okay, so there's a bit of a problem with this, is that the kind of overlap of the projection light cone of your second objective and the collection cone of your third is very limited. Although my cartoons may be a little bit exaggerated here, this is a general problem that needs some more observation. So you see here, this is the kind of shows the transmission between at O2 to O3. So for in this case, a high NA air objective, in the classical remote focusing type arrangement, you see no loss of rays through the system. This is great. But when you tilt things, then you start to not only lose rays. So this red ray is no longer limiting. This black ray now is the limiting ray. So this is loss of information, so loss of resolution and light throughput efficiency. But also the problem actually with these high NA objectives would be that they would actually just crash into each other with even a few degrees of tilt between the two, which makes this kind of arrangement unsuitable for imaging, for OPM. Some clever people realized at some point that if the sort of trick really here is to exploit Snell's law by introducing a higher refractive index media in the O3 object space to compress the ray cone that's projected by O2 over a smaller angular range. So originally Binyang in Bo Huang's lab had done this with, I think, with a water immersion lens, which I think was quite cumbersome. And then Alfred and Andy at Calico designed this glass-tipped zero working distance or solid immersion lens, which is, I think, a more practical solution. Also, the glass has higher refractive index than water, so it's more effective at this sort of compression job. So I think this is just a better solution, and it's obviously something that's taken off in recent years. So again, yeah, just showing this for if we use this this glass-tipped objective, we in the remote focus arrangement compress the rays over a smaller range. We can tilt the system all the way up to like 18 degrees, I think, without losing any rays in the system. So no loss of, in that case, no loss of resolution or light throughput other than reflection and so on. And absorption. But you do need to sacrifice some aperture to your light sheet generation. And then something like 25 to 30 degrees of tilt is generally considered a reasonable compromise. This gives you minimal loss of rays. So the black ray is still the limiting one. As we'll see, this is fairly negligible in terms of losses. And you get enough aperture for your light sheet generation to produce a suitably thin and long light sheet for what you want to image at this scale. So yeah, the next slide will be, this is it will be fairly familiar to several of you, I'm sure. So this is from a paper a few years ago, which I think was the first peer-reviewed paper to use the lens. Yeah, this is various data sets from the paper. You use a 100x 1.35 silicon oil objective lens, and you end up with a effective NA, it's by my calculations, of something in the region of 1.25 to 1.3 after this sort of losses due to tilt and so on. So that's fairly negligible, I would say. And you see the PSFs here for OPM, full width half maximum on the scale of about 300 nanometers. You lose a little bit in Y, that's general to OPM due to this tilt. And this is fairly comparable to the Betzig lattice light sheet microscope, or maybe it's even a little sharper than that. And also fairly comparable to spinning disc confocal with the same objective lens. So is this, like the question was, is this something we could reasonably implement for service at the imaging center? I'd say yes, clearly, but there's obviously a number of challenges. So I think Alfred and Andy had done a really nice job of putting out with their kind of preprints, a lot of optical designs and so on. But beyond that, there wasn't an awful lot of information on how to build something like this up. So as anyone would, I designed the kind of whole optomechanical scheme, also the control software and electronics and so on from scratch. So I'll show you kind of where we go, the design we came up with from that. So it kind of looks in a way similar to the SMLM, but it's, you know, this shows the sort of custom inverted wide field body. So it's got all the normal things, XYZ stages, yeah, lots of other components inside that will maybe become clear. We use the same 100x 1.35 silicon objective. We have a light sheet generation path. So this has we have 3 laser wavelengths for light sheet generation. So a lot of these, this is a shared path with a lot of the emission path, as you'll see. You have it's not fully implemented yet. We have the angular dithering of the light sheet for destriping. So this is fairly common artifact in light sheet. Motorized slits for repeatable control of the dimensions of the light sheet, which is kind of important for service, and some other kind of alignment features. This shows the emission path. So again, we have the 2-color image splitter here behind the third objective, this glass-tipped third objective. So in this case, we have a huge format kinetics, a CMOS camera that will give us side-by-side 275 micron fields of view for the 2 color channels. And actually, this is larger than the third objective can support in a diffraction limited sense anyway. So yeah, there's no real sacrifice to doing this. So this kind of came for free. For actual finding of samples, like I wouldn't recommend trying to do this with a very thin and short light sheet. It's quite painful. So we added epifluorescence module to this. So we have motorized dichroics and other mirrors that move in and out of the beam path to switch between OPM mode and epifluorescence mode. It's just so much easier for finding samples. Again, have this Bertrand lens, which I found so useful on the SMLM. So yeah, one thing that realized early on, also speaking with people who have, see some of you that have implemented this previously, is that the 3 high NA microscopes are really a recipe for drift and loss of focus, particularly problematically. So where possible, I've really limited degrees of freedom on optics. So everything is just kind of, where possible, bolted to the optical table, and there it will stay. There's a few exceptions to that, but where possible, it's minimal degrees of freedom. But even so, the focal drift tolerance between the second and third objectives is pretty small, on the order of like 100 or so nanometers, let's say, for diffraction limited imaging, a few hundred nanometers. So, and even for 1 degree of temperature change, we see shifts of on the order of like 1 to 2 microns, or about a micron per degree is what we see. So this is, even in our very nicely temperature controlled labs, this is too much. So I kind of built a focus locking system into the O2-O3 system. So it uses an infrared laser again, goes into O2 through O3, and reflects back off the same laser blocking filter that stops the laser getting onto the camera, and is then collected on a quadrant photodiode for, again, doing the feedback of control of the third objective piezo stage. Yeah, we want to do live imaging, so we have stage incubation, heating of the objective, motorized correction collar to correct for spherical aberrations, and so on. And yeah, also would like to try to use this for doing some volumetric localization microscopy at some point. So we added, or even just for imaging across large areas of a potentially slightly tilted cover slip or something. It's nice to have a kind of focus locking between the first objective and the sample. So I actually added a second focus lock system, which is exactly the same as what I have on the SMLM. Yeah, and this shows kind of all the beam paths all overlaid, and the system as shown in CAD. And this is what it looks like on the table at the imaging center. So you can see some of the features here, like inside the body, some of the stuff going on there, the second and third objective pair, the image splitter, and so on. So this has been up and running for about a month now. So yeah, so this is all fairly new. One other aspect of the OPM to think about is the deskewing part. So in general, with these kind of light sheet sort of microscopes where you are imaging tilted planes relative to your cover slip surface, then you, for kind of ease of viewing, when one is used to looking at kind of XYZ defined volumes relative to the cover slip, so XY in the cover slip plane and then Z like height above it, it's a little unsettling viewing, trying to view the data in this skewed format. So something my colleague Tsuchiang has been helping with is working on the deskewing workflow. So basically taking this sort of skewed oblique planes and putting it into this sort of more classically recognizable XYZ format. And then this is just basically the combination of three transformations. So shearing, scaling in one axis, and some rotation. So yeah, Tsuchiang has been helping with not only the implementation of that, but also the kind of automation of that in the kind of workflow of actually sitting down and imaging at the microscope. So can talk a bit about that. So the microscope is you have an acquisition PC, which is controlling the microscope through LabVIEW. So we have a few UIs based on LabVIEW. We have a National Instruments FPGA, which is doing all of the hardware synchronization through various analog and digital channels. So that's talking to galvos, cameras, lasers, focus locking electronics, stages, other things, I'm sure. So the acquisition PC is acquiring the skewed data, and it can write this at the full data rate of the camera. So it's maxing out at about 3 GB per second. Oops. Yeah, and then we have actually a second PC. So we offload the job of doing the deskewing onto a second PC. So the two are connected by a 25 gigabit fiber line. So the analysis has pretty seamless access to the data. And we can more or less do the deskewing in real time, as long as one isn't taking more than like huge volumes any more than every 30 seconds or something like that. So anything quicker than that, then of course there's going to be some waiting time, but we can still optimize various parts of that process. And then the analysis PC then offloads the data onto the EMBL file servers from a regular 10 gig optical fiber connection. So yeah, that's where we are with it now. Initial testing, I have some PSFs to show here. So actually on the left, you have the epifluorescence channel. So the noise in the data is really just, this is a kind of industrial camera used in this channel. It's really just designed for finding samples. So it's a little bit noisier, but right now the epi-PSF is not actually quite as sharp as it should be. So I'm kind of investigating why that might be right now. But yeah, the thing for right now is that the OPM PSF is pretty much in line in the non-tilted direction with the epi-PSF. And in Y, of course, we lose a little bit of resolution, and we're tilted at something like 27 degrees I measured. So yeah, there's still some optimization, of course, to do, but I'm generally quite happy with where it is at this stage. So we have some initial biological images. So we have these cells undergoing divisions. So here we have on the left is maximum intensity projections. On the right is just arbitrarily chosen single planes through the data. You see some lights, these sort of stripy light sheet artifacts in some places. That is something still working on. But yeah, you can see you have the Golgi in EGFP and histone M cherry in the nucleus. And you can see during the cell divisions, some of the cell divisions, you can at least resolve the chromosomes during the division. Okay, so that sort of just takes us to the more or less the end. So this is where we are with the system right now. The remaining challenges really are to work on the PSF of the first objective. So I actually want to compare against the same lens from another lab. I feel like we have some vibrations in the third microscope. And yeah, working on the de-striping. And then beyond that, it's the more sort of standard things for the service. It's like making it as usable as turnkey as possible, and providing training for at least the application specialists to sit down with the users. In terms of other developments at EMBL, my colleague Nihit is working on a cryo-single molecule localization microscope. So this is fairly big focus for the CLEM workflows, and then also my co-engineer Tsulun is working on adapting Robert Prevedel's Brillouin scattering confocal microscopy for external users. Yeah, just big thanks to all at the Imaging Centre, particularly these, and in the cell biology and biophysics section at EMBL, particularly all these people here. And yeah, also thanks to our industrial partners. So you see these down the bottom, the major partners we're collaborating with, and then all of our funders and sponsors at the top. And yeah, thanks for listening, and I'm happy to take some questions.
Great. Thank you very much, Rory. Very impressive engineering. The floor is open for questions. Yeah, Rito.
Hey Rory, really cool engineering on both the single molecule microscope and also on the OPM system. Just a question for the OPM one. Do you have any shadow reduction in your light sheet engine? Or is it straight up a spin light sheet without any dithering?
There's dithering, but it's not implemented yet. So it's let's say it's implemented, but it's poorly aligned. So turning it on basically tilts the light sheet out of plane. So slightly, so I need to just work on the alignment of it. But it should be relatively straightforward.
So is it like a resonant galvo in
It's a galvo. It's just a galvo
I see.
sync to the image acquisition.
I
Yeah.
think Jan Huysken called it M-spin.
Yeah.
Yeah,
Yeah.
okay.
Yeah. I don't know how, in my experience with light sheets, mostly been in embryos, and there you really notice the shadows. I mean, you'd probably be better able to say how problematic it is in these thinner samples.
Yeah, strangely, it also shows up in the thinner samples, at least for us. So when you have like a cytosolic label or something dense, you often see, I'm not sure if it's imperfection in the optics. I think some is induced from the cells, which is surprising, but yeah, okay, cool.
Great. Yeah. Anyone else?
I was a little curious. You mentioned that you were simplifying some of the electronics for the single molecule rig, but you didn't really mention much about that. So for dissemination purposes, how you go about, communicating more streamlined electronics.
Yeah, I mean, all I can say is so I wouldn't say we're simplifying anything. The major thing that predated my joining was this micro FPGA thing, which was published, a few years ago. So there's full designs available for all the boards for that, and we also then relink to that for the paper, and then you should just be able to send that to your kind of electronics fabricator of choice and have them assemble it for you and so on. And there isn't, well, have them assemble the boards at least, and then making connections between them. There's a full wiring guide on how to connect it all up. I wouldn't say it's the most easy of undertakings, but it is doable. And then beyond that, there's various boards for the focus locking, LED for transmission illumination, and controllers for that and so on. So yeah.
So then follow up on control. So you went from micromanager for that rig to LabVIEW for the OPM. And did you build off of an MTA from Howard Hughes or you started from scratch there?
started from scratch. I mean, LabVIEW is what I know, and that's sort of what I've always worked on. And I mean, there's some thoughts about in the long term what to run the OPM through, but the decision, at least initially, was just let's get something working with what I'm comfortable with. The micromanager was just because the software there was inherited from, you know, the other lab that's what they were working with. Edge, you really don't mind LabVIEW. It gets a very bad reputation, and when done badly, I think it's deserved. But you know, done well, it can be a nice tool. So.
So Rory, I had a question on the SMLM side. I think you sort of mentioned a little bit about aberrations, but then didn't go into much more detail. I think would be quite interesting, you know, for many of us. Can you say a little bit, you know, what the major causes and sources of aberrations are in the system, and how you typically deal with this, and how stable and varying they are from, you know, day to day to sample, you know? Can you say a bit more about this?
Sure. I mean, in terms of what we're doing with the system, everything is on very thin samples. So most of what we're doing is with a, you know, 100x 1.5 turf objective, and deep imaging means like 1 micron, 2 microns beyond the cover slip. So, you know, sample induced aberrations there's obviously spherical aberration gets a little worse as you go deeper. We generally just try to rectify that if we go any deeper than that, probably with the silicon objective and so on. So in terms of the actual aberrations that are important for us, it's for the kind of, it's generally field aberrations from the objective. So the objectives are good up to, let's say, maybe 50 microns from the center. So that's a really, that's what you can rely on because you have a high requirement for a field invariant PSF, particularly for the Z localization. You really can't tolerate that the PSF changes across the field of view even at all. But there's no active feedback in terms of, you know, there's no adaptive optics there or anything like that. But it's generally just you accept that there's some limitation on the size of your field of view for these, you know, really high NA objectives.
Okay, yeah, thanks. So.
Can I ask you, maybe I missed it, but do you have a motorized correction collar on the single molecule setup as well?
No,
or just on the.
Yeah, it's quite accessible on the SMLM, and honestly, I don't want that anyone touches it once it's in place. It's extremely let's say the Z localization precision is extremely dependent on the correction collar position, and once I've gone through the process of really optimizing it, then I prefer that people don't touch it. So yeah, I didn't want to motorize it.
Can I ask you for the other system, the OPM, what correction collar do you use? Is the Leica one, or do you have a?
No, it's a home built one. It's basically based on a small whatever, one of these little Robotis motors and a couple of gears and some 3D printed parts onto the correction collar of so there's a Nikon 100x 1.35 silicon lens.
So cool.
Thanks.
A sort of a very general question I have, you know, is a little bit maybe also interesting for everyone here, is sort of to which extent you go in sort of the engineering of the usability of the microscope. I mean, I think you had at the end one slide, you know, where you say, okay, usability turnkey, of course, you know, that the sort of the system runs, but then in terms of the users coming, is it then sort of that really the user itself runs 100% of the image acquisition, or is it still you and your colleagues, and how much sort of hands-on is it? Or hands-off is it? I should say hands-off from your side.
It's still a bit of an open question. And in terms of the custom systems, the SMLM has benefited from the fact that Jonas's lab was there in the past, and many people at EMBL at least know how to use Jonas's microscopes on the basis, you know, the software didn't change. For the OPM, it's a little different. I've tried as much as possible to keep it as user-friendly as possible, but it's not super easy to use. The intention is that everything is run by the application specialists and not directly by the scientists themselves. That's how it's working right now for example, with the MinFlux systems. That's sort of the main part of our kind of service efforts on the LM side at the moment, that the kind of relevant application specialist sits down and does imaging entirely with the users. So there's no kind of time that they're completely left to themselves on it. Which of course has its limitations in terms of throughput and so on, but yeah,